I like that better. All right, so this is our last topic is periodic trends, and yeah, has to do with the periodic table. You know, I put some pictures for the first two trends, and the other ones I didn't like any of the pictures, but if you like pictures, you can Google it. Atomic radius is really how big each atom is, and the trends are pretty much always diagonal, and they're this way or the other way. So atomic radius is this is going to be the largest corner, meaning down here, cesium, or actually francium. Um, and down here is the largest, and our smallest is actually helium. So the largest is there. And so the trend is as you go down the periodic table, you're adding shells. So that makes sense. So that increases the size. As you go across, though, they get smaller. And so the question is, why? Anybody have any idea of why as you go across the periodic table? So just going in a period. So if you look at like here, potassium and krypton, they're in the same period. They're both in the fourth row. Potassium is much larger. So why is it getting progressively smaller as we go across a row? As you go down a column, it gets bigger because you keep adding another layer, the 1s, the 2s, the 3s, the 4s, it definitely gets bigger. So anybody know why going across?
Is it because it's getting closer to noble gas?
No, that's a great guess. That will be an answer so on one of the other trends. It has to do with the nucleus. As you move across, you're increasing the nuclear charge. So what's in the nucleus? Somebody must know what was in the nucleus. It has protons and neutrons. So there's more protons. So nuclear charge is the protons. So as you increase the number of protons, so if we look at potassium, potassium has 19 protons. When we get to krypton, there's 36 protons. They're both in the fourth shell. They're both four layers out. Every electron has an attraction to the center. So an attraction to a plus 19 versus a plus 36, that plus 36 is a greater attraction. So it sucks the electrons in a little bit tighter. And actually, you can see it's actually quite a bit different. It's almost half the size as it goes across the period. So it's as you go across the period, it gets smaller. And so that's why the trend is moving this way and down, it gets larger. Does that make sense? All right, so then the question is just comparing them. This trend we keep coming back to because it ends up being part of our answer to a lot of the other ones. If you're comparing sodium and potassium, they're in the same family, the one that's lower down, and you would just say higher shell. If we're comparing sodium and magnesium, we're going across the periodic table, so sodium's the larger one. And that is, it has a smaller nuclear charge. Or fewer protons, you can also say. And that is, I think Christian was one of you mean that. Sorry. If I'm wrong, somebody about protons. All right, ions are interesting. So this picture, they're always like an optical illusion. The atoms are gray. So neutral is gray if you print in color. So gray is neutral. And so the green is the cations. And cations are positive. What does it mean to become positive? What happened for a cation to become positive?
Lose an electron.
You lose electrons. So this goes back to a question Major had asked me, I think, before class. So your final celebration is next Tuesday. It does focus on everything since celebration 2. The last page has a little bit of review that we'll do. I didn't write a full review because your teacher's also getting fatigued, and you have plenty of stuff to go back and review. But it is over thermodynamics, quantum stuff, and periodic trends. However, to be able to do this stuff, like the quantum and stuff, we do have to understand the idea of cations and anions. So some of the basic stuff that we've gone over, or you have to be able to use a periodic table. So when I talk about tin, that you're not Googling what is the symbol for tin, that hopefully now you go, well, tin is a sin, it's SN, you find it, and it's not so scary. The numbers on there are not as scary as they may have initially been. But cations lose electrons. When you lose, this is like you and me, when you lose weight, you decrease in size. Why, though, is it such a big difference? What happened when we went from lithium to a lithium positive is it loses a whole shell. It's more than just that they're losing electrons, they're losing a shell. Even the ones in the middle, remember we talked about the question about titanium? It lost the 4 S's when it became a +2. Most of them like to be a +2, so they lose this outer shell, which is the 4S, the 5S, the 6S, the 7S. So they actually drop down quite a bit. And that's what this picture is trying to show from, so cations always get much smaller. So the anions are the purple ones. And the anions are negative, so they gain electrons. And so what's going to happen when you gain weight, this is like the COVID effect, they actually get quite a bit larger. So they increase in size because, going back to the explanation from above, you're increasing the number of electrons. You're not adding shells, but the protons stay the same. So there's no change to the nucleus. So that nuclear charge didn't change, and that actually makes a big difference. And so you can see they go up significantly. The more you gain, the bigger they get. So the most dramatic is with oxygen versus fluorine. They both get bigger. Oxygen actually gets even more bigger. And that has to do with fluorine because it has a larger nuclear charge. It's just not. And same with here, positive. The more they lose, the smaller they get. All right. So if we were comparing sodium and magnesium, put the charges on them. Sodium is a, you guys all know your charges. Look at your periodic table. If you're asked for ions, it tells you ionic radius. So you find sodium +1, magnesium's a +2. Make sure you look where they are on the periodic table. So which one's going to be even larger? Sodium. So they both lost, but sodium is going to be larger because this one lost more. And also the nuclear charge. All right, oxygen and fluorine. This is a -2. This is a -1. So the O -2 because it gained 2. This one because it lost only 1. But they both lost their shell. So atomic radius trend is very clean. It's like perfect as you go across, as you go down. Ionic trend, though, it has to do with how much they gain and lose, and also with the nuclear charge a little bit. All right. Question. Magnetism. So what's paramagnetic mean? That should say para. There should be an A there. Or what's diamagnetic? Anybody? You can all write down your definitions. Diamagnetic is?
No unpaired electrons.
Yeah, so it's 0 unpaired. And paramagnetic. So the more unpaired, the more paramagnetic. And this is why iron has a special state of magnetism, because iron can have quite a bit of unpaired electrons because it's in the middle of the Ds. These guys down here, again, it was a question some people had asked me last week. I usually don't have you do orbitals down here because it's different answers depending on whose theory you're following. But these guys are called the rare earth metals. They're also the expensive ones. They're expensive because they're not common like the regular earth metals up here, but they have really funky magnetic moments because in the Fs you can have a whole bunch of unpaired. So really good headphones usually have a couple of these elements in them because of that potential, and it's because they're in the Fs. Anyway, kind of cool stuff. There's really cool stuff they do with ceramics too with a lot of these because of the paramagnetism. All right, so we're just figuring out if it's para or dia. So magnesium, I'm just looking at the periodic table. And this is where, so magnesium, if you're at the end of a block, magnesium is going to be 3s2. If you have both electrons in the s's, all the earth metals are going to be diamagnetic. Sodium is going to be 3s1, which means it's an unpaired electron, so it's paramagnetic. So you can always go look at the HEO. This also goes with, and those you had Chem 151, there's, in Chem 151 and Chem 104, we actually teach electron orbitals before we do ions, but sodium is a +1 charge because it loses that one electron. Magnesium's family is a +2. And so we teach you the electron orbitals to understand the ions. In this class, we go with more traditional, which is the ions were known before the electron orbitals were known. We also have to wait until we have an understanding of thermodynamics to be able to truly look at a little bit more detail of quantum mechanics and stuff. But that's why the class is taught in different orders. Any questions from that page? The biggest one, yeah. All right. So reactivity. Reactivity is a really interesting one. The reactivity, the trends tend to be either towards one corner or this corner. And this is the thing that's really interesting. When you're in the metals, the reactivity increases moving towards francium. So going within the 1As, the classic reaction is that reaction with water. And several of you had alkaline metals when you did your presentations way back. It seems like forever ago, but they become more and more violent with water when you drop them in. So starting as a metal, sodium metal, potassium metal, I think somebody did cesium, and that's the one where they have to throw it. They will use a crane or something because it will blow up the bathtub. There's Mythbusters did one with that, and they blew up something, a hot tub or something with one of the, I think it was with cesium. Over in the nonmetals, it's opposite. It's at the top half. So fluorine is the most reactive of all of them. And it has to do with the behavior, and it does go back to some of the stuff we were doing there. So with that, we look at ionization energy. Ionization energy is the energy to remove one electron. So who's going to have a high ionization energy? Who does not want to lose an electron? And who's going to have a low ionization energy? So any thoughts on that? Just going back to everything you learned. If you look at your periodic table, think about sodium. Does it take a lot of energy to pull an electron off of sodium? Not at all. It's like the lowest one of them all because it wants to lose one. It's like, yes, please take it. Magnesium is a blip in this trend, but we're going to see that this side of the periodic table is low because they want to lose an electron. And as we're going across, it becomes much higher. So high IE, because they want to gain electrons. So fluorine is going to be the highest. As far as size, so the trend is moving towards that upper corner. As you move down, you're adding shells. And so the distance is getting further and further, so it's easier to remove an electron. So since it's further from the nucleus. Punch my word in there. So this is going to be lower. And that's true anywhere on the periodic table. As you go down, you're always adding shells. And so their ionization energy becomes lower. The trends are not very pretty on, not like the atomic radius, because there are going to be blips. But the highest ionization energy is going to be fluorine. Now, I guess this is something, I don't know how they measure it. Those of you who've had me for a class before, when we start 222, the first 1/3 of Chem 222's theme really is molecules, that we're looking at molecules. And so we'll look at something called electronegativity. And I mentioned electronegativity this term. Electronegativity is their desire or their greed for an electron. So that is a term that came from Linus Pauling. And Linus Pauling was all about molecules. He was a biochemist like myself. This is a different view of it. They're looking at the energy to remove an electron. I don't know why. Right, there are blips. It's not a smooth trend. That's why I didn't show a picture, because it's really bizarre. Anybody got an idea where a blip might be? Like where an unusually high ionization end somebody does not want to lose? Like other than at the halogens. I don't think they actually give a number for the noble gases, because I'm not sure you could remove an electron. But I guess maybe it would go to helium. So I apologize, because the noble gases. So our trend would move towards helium. I can't remember now if they actually give numbers to the noble gases. So the blips are at the 2As. They have, it's actually very high. It's not the highest. Why would the 2As be very high? There is something I didn't teach you. So there is a generic way to show to show atomic or electron orbitals. So this whole family, they're always going to be S2. They're always, you can't see that, sorry. They're always going to have 2 electrons in the S's. So we say NS2. The N number could be 2s2, 3s2, 4s2, 5s2, 6s2, 7s2. With the 1As, we would say NS1. So it's just a generic way of saying it. But the 2As, because they have a full subshell, full subshell is very stable. They do not want to lose an electron. They're like at a place that's beautiful. It is not the same as being here. This is much more stable. Having the P's full is a place of stability. Having the D's full is another place of stability. I'll get to that in a moment. All right. So that's one of the blips. The other blip is, I'm going to call it the 5As or nitrogen's family, when we get NP3. And what's happening there at NP3, so this is like nitrogen, phosphorus, arsenic, etc., is you have, really missing having a board where I can make a mess. A half full subshell is very stable. So the trend is not a smooth trend like the atomic radius trend, which is part of why I didn't show it. And I'll say I don't show it nice with little balls like the other one did. So there's blips. At the 2A, it goes really high, and then it comes back down. You see this gradual increase. And then at nitrogen's family, again, I call it the 5As or it's the 15s. And having that half full, it goes quite high. And so oxygen's actually much lower, which is kind of seems really weird that it'd be easier to pull an electron off of oxygen. So I want to mention the D's. Usually this is talked about with the S's and P's, but I want to, since I'm thinking about it, it's something I ran out of time last week. There's a couple blips in the D's that happened. And this ends up being something that became really important, and it's with Nickel's family. So with nickel, palladium, and platinum, these guys are actually the most stable place on the periodic table. They're actually more stable than the noble gases, and they are called the noble metals. So why? I mean, they're not at the end of their block. I mean, zinc, cadmium, and mercury, they would be the ones that have the full subshell. They should have that blip of stability. Why is it? And they do. They are more stable than copper, silver, and gold are desperate because of where they are. They're one away. They're like in between the perfect lands. But why are nickel, palladium, and platinum so super stable? Well, if we let's look at palladium. Let's do palladium's configuration. So if we did palladium, we'd start with krypton. Right, so previous noble gas. And then after 36, you come to 37 and you would write 5s2. And then after the 5s, you would go to 4d. And then you count over and it is 8. This is where something very unusual happens. And I believe I mentioned it with silver last week. But with silver, they're at an odd number. Odd numbers are never as stable as even numbers. What happens with this group, with palladium, platinum, and nickel, and especially palladium and platinum, nickel is kind of funky, is it actually takes those 2 electrons. And that's what palladium's configuration is. I usually avoid palladium on like your celebration and stuff, but it's worth mentioning here. Why does this make it more stable than cadmium? Well, if you go back and figure out what krypton is, krypton had the 4 S's and the 4 P's. Now we have the 4 D's full. You actually have a full shell. Right here in the noble gases, where this is stable, but these guys technically they're not full. The 4 P's, what about the 4 D's? But here with cadmium, when you get this 4D filled, well, actually you've already opened the 5 S's. Well, I just took away the 5 S's. They're gone. They don't even exist. If there's no electrons there, it doesn't exist. This makes it extremely stable. And this is why palladium and platinum are extraordinarily expensive. I cannot believe people wear them as jewelry because they are extremely valuable for things other than making us look pretty. This is why your car gets broken. The catalytic converter in your car, which is underneath your car, it's a catalyst to change. Our car combustion is not perfect, and it makes a lot of carbon monoxide. So the catalytic converter changes the carbon monoxide into CO2. So the CO2 pollutes the planet, but the carbon monoxide would kill us because it binds hemoglobin so well. And so the catalyst is palladium or platinum. And so drug addicts go around and take your catalytic converter, get the palladium or platinum, go and sell it, and nobody follows it, nobody can track it, and you come out and you don't even realize your car still works, but it's polluting. And yeah, all right. Anyway, so that's why they're called the noble metals. Let's go back. The trends are usually asked about in the S's and P's. There is more with the D's too, but there's that. I mentioned with chromium. Chromium actually pulls 1 over, so it has all unpaired, which gives it an interesting configuration. This is all theoretical because I'm not sure if there's any way they could fully test it. So these two are blips. Ask about on your worksheet. You just write that there. All right, this is the energy to remove the second electron. So the first ionization energy is the energy to remove 1 electron. Now we're going to remove a second electron. So who is going to have a really low one and who's going to have a really high one, and why? So think about what you know about the periodic table. Any guesses? It's not a nice smooth trend either. Well, let's look at the 1As. Are they going to have a high or a low second ionization energy? Got 50-50 chance. So this would be great if I knew how to do the polling, which I don't know and I don't care to learn. I could see, you could all like pick, I would know who's actually here, but I don't really care. So, so the 1As, they want to lose sodium. It wants to lose 1 electron. It loses 1 electron. It's now like neon. It's perfect. It's happy. It's in bliss. Is it going to want to lose another one? There is no way it is going to allow anything to get it out of that bliss land. And so it's extraordinarily high. You can pick your favorite adjective. So we're going to say it's extra high. Because it does not want to lose 2. It does not want to end up like a halogen. Halogens are as miserable as the alkaline metals were. So let's look at the 2As now. The 2As were a blip. They were really stable. They had really high first ionization energies because they had a full subshell. They do not want to lose 1. But if you came and said, hey, I'll take both of them, they're like, really? Are you serious? Because now they're not at a full subshell. So if magnesium gets a +2, it lands in the land of bliss. So this is not a blissful place. It's much happier than next door, but still have contentment. So the 2As are extra low. Something to ponder. And the whole middle is extra low. They all love to be +2s. Because they all love to lose both S's. So loses 2 electrons. All right, so first ionization energy, which one is larger? So sodium or potassium. As you go down, it's easier to pull them off. So it's sodium because of the smaller radius. And sodium or magnesium, magnesium, because it doesn't want to lose 1 electron. All right, and then second ionization energy, sodium, because it does not want to lose 2. And questions. So your last study said I made it due next Tuesday because you guys probably, I mean, you have your presentations on Thursday. We'll talk about that in a moment. And as Max was saying to me, most of your classes start loading like a lot of stuff due this week. So I made it due next week on Tuesday. I will either record myself going over it or I'll just give you the answer key. So you want to try it and then you just check it and turn it in. So it's a give me 5 points. And then there's a worksheet that will be due. But if you have the notes and you look at your study set, you'll be fine. All right, electron affinity. The word affinity means attraction. So it's an attraction for the electron. It's actually worded more complicated than that. It has to do with an enthalpy of attraction. Here we go. You may remember that word. So enthalpy was the heat change of the attraction for the electron. So instead of losing an electron here, pulling it off, we're now attracting it. So the trend is similar, that the ones that are going to have the highest attraction are going to be over here. Fluorine is going to have the highest attraction. Now, this is worded different in different places that you look. It is technically a negative attraction. And so it's who has the most negative attraction would be the highest. So it's the most negative enthalpy change. Yeah, remember delta H's. All right. But the trend is that way. Again, you're going to see weird blips that nitrogen doesn't want another one because of that. So you're going to see the same blips. So nitrogen, because of the 3 unpaired. So 3 unpaired is stable. So nitrogen is really low attraction. And the one next door to it, which seems really weird, is they're looking, the problem with all this is we're looking at everything very monoscopic. That carbon would technically have a really high one because it would want to get to where nitrogen's little la-la land is of 3 unpaired. 3 unpaired is a blip of like a stable, it's stabler than next door at oxygen. But saying you're more stable than oxygen is really not saying much, because oxygen and fluorine are the most miserable elements on the periodic table. They are so reactive. They are oxygen's what drives our life. So again, in the pair, it's going to be the same answers above. Sodium technically would, because it's smaller radius. Seems really weird. But that smaller radius means the center. And then versus sodium or magnesium, magnesium would not. It has a full subshell. So it's not going to have an attraction. So the sodium technically would, because it has that unpaired. Yeah, I usually ponder it. All right, so again, study set 15 and worksheet 15 are due next Tuesday. So what is today, the 9th? So they're due Tuesday at 6 p.m. They are both due at 6. Well, you want to do them before your celebration. You can do it before that. You can do it tonight, get it over with, and submit them. And you can do it before Thursday. On Thursday, I'm hoping our groups, I wanted to talk about that. And actually, I'm going to pause in a moment. Let's look at the next page because I will talk. So Thursday, next page is some review for quantum. So Tuesday next week, the 16th, is our celebration 3. And it's going to be similar format, so 6 to 9 p.m. It will show up. I'll be on Zoom. It is over thermo, quantum, and the trends. We'll have just a little section on them. So that is study sets 11, 12, 13, 14, and 15. And the worksheets and your labs. So I did not make a review. Well, we'll go through this because the quantum usually needs reviewing. I would tell you to go back and redo your study sets. Just redo your study sets. You can redo your worksheets. There's a bunch of you who owe me. So lab 8 and lab 10 is due by Sunday. So there are several of you who did not turn in lab 8. You got to get that in. And lab 10 is due Sunday. You have a 7-day challenge. So hopefully you started it. I talked about it last week. If you didn't start it, then you're going to be turning the lab in late. This lab, by the way, has 3 parts. So the one part is math. It's Thursday. There probably will be time with some of the groups that if you have questions. So Thursday, all that we're doing Thursday is your class presentations. And you almost all of you signed up. So your presentations are either 2 to 4, 4 to 6, or 6 to 8. You have all shared your screen, so you all know how to do it. It is the same Zoom link for all of them. I will be in there the whole time. If you come early and I'm not letting you in, it just means the other group hasn't quite finished. Do come like a minute or 2 early because we won't start until you're all there. So especially the first group, like I'll be there 15 minutes early, 10 minutes early. So all of you come like 5-10 minutes early so we can start. So this last page is review of quantum stuff, but it's going to be show your work like the other 2 celebrations. Yeah, you should all be fine. If you have missing stuff, get it in. I'm going to stop recording. I'm going to pause, give you a chance to do this because I want to make sure everybody knows what they're doing on Thursday. I've had like 2 dreams in the past week that were like very vivid dreams, and they both involved nobody had masks on anymore. So I'm thinking I'm going to end up like a prophet here.
Yeah, that's a very good sign.
So it is a wonderful sign. So again, next Tuesday is our final celebration. We're all going to end strong. I'll put this, yeah, let's just all end strong. So, and I know, again, I just gave you the thing that if you have a late lab, let's get it in. Let's all end strong. If you have late study sets, everything in next Tuesday. Your papers are due when? You know, you can get them in early. Your guys' papers, they're like last time, 3 to 5 papers. They're due by Sunday, but really you do your presentation, you can get your paper in early, and that would be wonderful. You are doing peer reviews again. So you just write notes and submit that, and that gives you 15 points. That gives us all a boost going into that final celebration. So we're going to do it. We're going to make it. All right. So there, I did not, again, because your teacher's running out of steam too. I didn't make another page of practice problems. Go over your study sets, the specific heat stuff, go over that lab 8, go over the quantum, the worksheets and stuff, and we'll probably get done early tonight. So I'll stay after to answer questions. Next Tuesday, I will have an office hour from 5 to 6. And yeah, and today I'll stay after. So if you have questions on the worksheet. So longer wavelength. So Roy G. Biv. The red end is the longer end. The violet end is the higher energy, higher frequency. So here we go. See if somebody else can answer this. And that's all right. Nobody does. What has a longer wavelength than red?
Infrared.
Infrared. You're already up there, Tristan. But thank you for answering. Yeah, you guys can answer if you're already up there. You just don't get to be up there. And what's longer than infrared? Does anybody know? It's probably in all of your homes or apartments.
A microwave?
Yeah, microwave is, so the story of the microwave, I think I talked about in the video if you watched it, is microwaves, these are what are used for communication. So beyond microwave, but microwave, the guy they were using it for communication in World War II, and you have to have a chocolate bar in his pocket, and it melted while he was working with communication stuff, and he realized, and they invented the microwave. But beyond that is the radio wave, and that's where you get into how the whales and the dolphins and stuff talk, which is pretty cool too. And then beyond here, beyond violet is where the damage starts. So on the other side of violet is the ultraviolet.
X-ray.
Yeah, thank you. And gamma rays and all that stuff. So like what happened in Bruce Banner is the gamma ray issue. You don't want to have the gamma ray issue. All right, number of nodes. Number of nodes is the L number. So D would be 2, because that goes back, writing down your SPDF. So again, the 1357 is the number of orbitals, and then we were writing above 0, 1, 2, 3. That's the number of nodes. That's where this number came from. Go back and redo your study sets. Just go back, print those 5, or just pull them up and go through them again. Yeah. All right. Which quantum number describes shape? We just talked about that. That is the L number because of the nodes. Tells you how many nodes they are. So it gives you the shape. And again, electrons are not behaving how the models all show them of them running around. They're like pulses. So we talk about them like a wave, but it's more like a pulse. All right. Is energy emitted or absorbed on number 4? So if we jump from N1 to N3, we're going from inside to outside. So when you move from inside to outside, you have to absorb energy because it's moving outside has higher energy. All right, and then the next one, you just look to make sure they're good, which they are. And so this would be a 4D. Which is really cool when you think about it. When this starts just clicking, it's really awesome because this is quantum mechanics. And then you have to go back to that quote from Bohr where it says, if you think you start understanding this, then you don't understand it. That holds true for everything. All right. Maximum electrons in the D. So there's 5 orbitals. So it's 5 times 2, which is 10. So maximum means 10 is the most you could have. It doesn't mean you always have 10. And then manganese. So you find on your periodic table, it means you need to know the symbol of manganese. So what is the symbol for manganese? It is
Mn.
Yeah, so I don't remember who, somebody did manganese. I think it was Kyle. Mn. So magnesium and manganese are actually found very often together in nature. And it does come from an area of Greece, I believe. So Mn is here, and it's in the D, specifically in the 3D. So it's a 3D. And what subshell? So you tell me the shell number and the subshell, so the 3D. All right, on number 8, the third principal energy has how many subshells? So when n equals 3, there are 3 subshells. The answer is 3. And that is because the L number can be 0, 1, and 2. So Spencer, this is kind of the question from earlier. These actually then correspond to SPD, but they are saying what is possible. So if n equals 3, L has 3 possibilities, and we just gave those then letter designations. All right, 4F, 7 orbitals. And that goes with the ML, -3, -2, -0, 1, 2, 3. There's 7 possible. Those ML numbers don't really mean anything. It just means there's 7 possible. And then it just fit to the periodic table, which was pretty cool. He did not write the equation to go with the periodic table. He just wrote the equation trying to understand some of the properties. And yeah. All right, after the 4D. So your periodic table has all the answers. So the 4D would start with deuterium, and it would go to cadmium. So what comes next? The 5Ps. So it's all, the periodic table gives you the correct order. So the 5Ps. So again, the 4Ds are deuterium to cadmium, and then we go into the 5Ps. Any questions 1 through 10? So your test this time, there are going to be the fill in the blanks. So that's kind of what this page would be. But there will be all the math. There will be the electron orbitals. Yeah, you'll be fine.
What did we say number 3 was?
L,
L, okay.
because it describes how many nodes, which gives you the shape. All right, which is highest? You look at your period. Actually, this one's pretty easy, the 4F. So there's 2 ways. One is with your periodic table, 3Ds here. The 4F is technically here. So remember, it's not actually down here. It would just make the periodic table super long. And so whichever one comes furthest on the periodic table. The other way is you take the N plus the L number. So 5S, you would get 5 plus 0, so you would get the number 5. 4F, you'd have 4 plus 3, so you get a 7. And 3D would be 3 plus 2, which is 5. If they come out as the same number, the higher N number wins as the higher. All right. Maximum electrons that can occupy any orbital, 2. That goes back to the whole MS. It can only be plus or minus the two directions you can spin. All right, valence electrons are the outer electrons. So the core electrons, when we were drawing orbitals, that's what these, the krypton or the argon, those represent core. The core electrons are not involved in chemical reactions. Valence electrons are the ones that are chemically reactive. So it is anything after the noble gas. So after the noble gas. And so for phosphorus, it should be 5. So you can, we're here at neon. So 1, 2, 3, 4, 5. There was a trick I showed you back in the very first, when we first did cations and anions, that one video. Their A group number gives you the valence, but this has 5 electrons after the noble gas. Oh, here we go. Number 14 is what I was talking about earlier that I hadn't shown you this until then. The generic for halogens. So halogens are over here, fluorine, chlorine, bromine, iodine. And what they all have in common is they all will end with P5. They will all have 5 electrons in their p orbitals. So how we fully write it is we say N P5. The N can be any number except 1, because there's no such thing as a 1p. And so we actually say NS2 NP5, because so for fluorine, it would be 2S2 2P5. 3s2, 3p5, 4s2, 4p5, and so on. So that's what it means by generic, is the N number can be anything from 2 on, and then you would have that. All right. So the halogen in the third energy level means we're at 3p. So not the third halogen down, but this would be chlorine. So just be careful. Usually when I'm asking you, I actually underlined it there. I want the name. So it is Cl, and so just you would tell me, hey, that's chlorine. So the very first celebration, there were questions like this. It just wasn't with quantum theory stuff, but where you had some fill in the blank kind of stuff. All right, chemical properties similar to oxygen. This was a question on the first celebration. I don't think it was with the oxygen, but what are we looking for that question? Properties similar to oxygen. Yeah, family. So Mendeleev put them in families first because they had similar chemical properties. Quantum mechanics shows why. So if we go back to question 14, the whole family ends up for the halogens at NP5. So they all have 1 electron to go to be perfect. For oxygen and sulfur, they have 2 electrons to go to be perfect, to become like neon or argon or selenium or tellurium. And so the electrons actually show why that chemical reactivity is like that. It doesn't matter which comes first, right? All right. An element with only 2 3D electrons. This is also implying that we're in the ground state. I don't keep saying that because, in my humble opinion, questions with all these extra words end up confusing most students. So the 3Ds are here. 2 electrons would be Ti, which is titanium. And all right, gallium is Ga. I think Jeremy did that one for his element last time. So gallium, and gallium is a metal. So again, those were technically things we did way back, but you might run into a question like that. And it's not meant to trick you. If it's below the line, they're metals. That is actually a trend. It did show up on that page. Let's go back to our trend page. Yeah, it should have been down here. I apologize. There is actually another trend, and it is called metallic. And I think there is actually a question on your homework. So the metallic trend, and the trend is as you move down to the lower corner. So as you move towards the metals and down, so towards francium is considered the most metallic of all. And that's actually really interesting. 2 of you did, Christian did francium as his element last term, and Tristan did it this term. Francium only exists for like 21 minutes, its half-life. So how would they even be able to tell its metallic properties? But as you move towards the left side of the periodic table, and as they become larger, more shells, they become more metallic. The non-metals, of course, are above this line, and then the metalloids for boron, silicon, arsenic, germanium. So, all right. Unpaired electrons in cobalt. So look at the HEO. You don't have to draw the whole electron configuration. So you can go, here's cobalt. Some people get it right off that there's 3, but you can always do it. All right, so it's configuration. You go the long way because some people it helps them. It's going to be in the 3D, and we would count 1, 2, 3, 4, 5, 6, 7. That it would be 3D7. So if you drew out the orbitals, I do find, rather than guessing, some of you see how it is without having to draw them, and that's awesome, that you would have 3 unpaired. So the answer for 19 is 3 unpaired. So there's 3 arrows that don't have a pair. All right, and then argon. So argon is Ar. It is a noble gas. It is perfect. It is going to be diamagnetic. So what families are going to be diamagnetic on the periodic table?
The nobles.
Yeah, I don't know who said that. Who said that? You were right.
That was me, Christian.
Oh, okay. I thought it was you, but it wasn't. What other one? Sorry, I thought my
Earth metals.
Yeah, the earth metals. So the noble gases, the earth metals, the ones that are at the end of their block. And so this is the thing that's really cool. Mendeley's periodic table puts zinc, cadmium, and mercury with the earth metals because they behave like them, because they're at the end of the D block. And so that's why the 2A's and the 2B's. That's the traditional way. Mendel, I don't know who did it, but that's why the B's are numbered like that. The 1B's, copper, silver, and gold, were put with the 1A's in his periodic table. It's worth going and finding a picture sometime. And it's like, you see how much you learn. Somebody was talking to me about that like a week ago, and it really is that they started, they were watching a documentary or something, and they're like, I actually really understood all this stuff. So we get so involved in all the nitty gritty and doing stuff and just sit there instead and go, wow, this is really cool. I have this greater understanding of, like, I don't know, some book you're reading at some point in 10 years. And it's like, it's not that big of a mystery anymore. All right. Highest energy occupied orbital, that means the HEO. And again, hopefully now you all know sodium is Na, and just label your periodic table. It is the 3s is its HEO. So whatever its defining block is, right. So the S's and the P's will go with whatever row you're in. The D's are off by 1. And again, the F's are off by 2. So the 4 F's are in the 6th row, and the 5 F's start with thorium, and they are actually in the 7th row. All right, we're almost done. So this is a good question. This is like a question. These next ones are a little bit more challenging, but some of the questions on your worksheet. So 2 unpaired 3p. So you can always make a sketch. So 3p, to have 2 unpaired, you'd either have to be 3p2 or you'd have to be 3p4. Oh, it's Tuesday night, isn't it? All right. 3p2 and 3p4. Sorry, I heard my son talking and I realized why. So 3p2, here's our 3p would be silicon, 3p4 is sulfur. So our answers are silicon and sulfur. Goodbye. And all right. What element has 10p electrons? All right. Well, 2p6 would be 6p electrons. So we need 4 more, so then we'd have to go to 3p4. So 3p4 is sulfur. Fire and brimstone showed up twice. Oh my goodness. I think I mentioned it in the BS video. The study that was done with AIDS patients, looking at survival with cancer patients too, is totally related to our view of creation. Do we see it as fire and brimstone and you've sinned, or loving and forgiveness? Ponder that. All right. Really changes the viewpoint. What element is represented? So when you excite them, anything is possible. So you just count 2 plus 2 plus 2. There are 6 electrons. This is carbon. So normal Normally carbon would be 1s2, 2s2, 2p2, but when we excite it, those two electrons, they can go anywhere. They could have gone to the 4f. What the heck? They can go anywhere you want to put them. So you just count your electrons. And then number 25. Oh, this is what we did today. So we find where we are in the periodic table. Rubidium, so we're here with these four, and so it's the lowest corner, just cesium is going to be, oh, sorry, that's the largest. So that would be the largest. That is not my answer. So read the question before you answer it. That I did that on purpose, right? I caught my mistake for a change. And so the smallest, so as you go down to that lower corner, they get larger. So that's the large. So the upper corner would be the smallest. So it must have been strontium. That's the smallest. And again, it has fewer shells, higher up, fewer shells, and the more to the right, higher nuclear charge. All right, any questions? All right, so thank you. You guys are all awesome, and I look forward to Thursday. You have a worksheet due tonight, so don't forget, and I will stay around to answer questions.